This is the confusion matrix. Okay. You don't want any false positives. You don't want any false negatives. Okay. I hope these topics were clear from yesterday's lecture. So today we'll start with the naive-based classifier. So it is a probabilistic classifier, and most of them, they have this is very well known as the ideal classifier. Okay, it is dependent on Bayes theorem. You might have learned it during your probability class. So here we have this formula. Okay, you can look at it this way. This is what you call as the class condition probability, conditional probability. What is my probability of event Y occurring given that X has already happened? Okay. And this is how you evaluate it. This is how you get this probability. And what Bayes theorem tells you is, okay, um, without so this will be P of Y. This is known as your prior evidence. Without observing anything in X, uh, without observing anything in X, what's the probability of event Y happening? Okay. Once X has, that specific event for X has happened, you again change your probability according to this formula so that this becomes your posterior probability. X has already happened. Okay. Now that X has happened, how is my probability of Y being changed? Okay. This is the essential theory behind naive Bayes classifier. I'll tell you later why is it called naive Bayes. Okay. And yeah, this is one of the popular examples, statisticians and machine learning people use in the context of Bayes theorem. So you you want to go to a clinic and take a test, okay, if you have diabetes or not. The overall probability of you having diabetes is 5%. Okay, that would be your prior probability P of Y. Okay, if he or she obtains a positive result from the test, okay, this probability, prior probability, that is P of Y here, you know is updated to account for additional information here is the result of your test, that is X. Okay, we take into account this additional information, do this calculation and update our belief. Okay, then it becomes your posterior probability. So yeah, so X here denotes this random this is an event that denotes the result of your test. Okay, Y here denotes the result, of you having uh, diabetes or not. Okay, actually having diabetes. This is your result from the test. Moving on, how actually do we implement this naive Bayes classifier? Okay, first step is to calculate the prior probability. I'll be showing in the next slide how do you execute all these steps. Okay, calculate the prior probability, find likelihood for each with each attribute for each class, put it in Bayes formula and calculate the posterior, and you see which class has higher probability given the input. Okay, uh, so yeah, this is the example. So here you have the weather. Okay, so this is your feature. Okay, you just have a single feature here, and you have your label. Okay, given this weather, will I go uh, to play or not? Okay, if it's sunny, I won't be playing. Or these are many data points you gather from different individuals. Okay, and yeah, first step that you have to do is convert it to a frequency table. Okay, for different weather conditions. If so, what's the these are different weather conditions, and this will be whether you'll be playing or not playing. Okay, for if the weather is overcast, do you have any data point that says no? You can check here. Overcast, yes, 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 yes. Here there is no data point for no, so you keep it as zero. Okay, this is for you have four different yeses, and similar case you calculate for different weather conditions. Okay, and you calculate the total of no's and yeses. Okay, what you do here again is after getting this frequency table, you calculate the likelihood table. Okay, in this likelihood table, what you do is for each, let's say, mm, so whenever new data point comes, okay, let's say you want to estimate the probability of playing, yes, okay, given that the weather is overcast, okay, you simply do 4 by this total 9, you get the probability of 0.44. Okay, so if someone asks you whether you will go out to play given that the weather condition is overcast, okay, that probability is 0.44. Okay, and the probability for no is 0. Okay, you have to check which one is higher, the probability for no or probability for yes. Okay, which one is higher, that will be your label. Here 0.44 is higher than 0. So if the weather is overcast, you will definitely go out to play. Okay, and so again, if someone asks you whether uh, you will be playing, or probability of playing is whether you go out to play, whether the forecast is sunny or not. So again, you have the frequency table here. This is for a single feature I'm talking about. You have to do this for multiple features at once. Okay. Here again, you have two no's, three yeses. Okay. You calculate it by the total. So zero point 0.4. This is 0.33. So when the weather is sunny, since this probability is higher, okay, since this probability is higher, I won't be going out for playing. Okay. Again, for the rainy forecast, again, the probability for no is higher. So again, I won't be going out to play. Uh, I think this also might become more complex if I put in other features also. Any doubts in this? Should I explain it again, or is it clear? Oh, table one. So here you are estimating the priors. Okay. I think you don't need to worry about table one. Table two is fine. Okay. Table two is actually what matters. So here you are calculating your priors. Priors in the sense P of Y. Okay. This is P of Y here. So that will be total number of no's and total number of yeses divided by the total number of data points you have. That is 5 by 49 by 4, 0.36 and 0.64. Okay. Yeah. You don't need to worry about table one. Yeah. So, in summary, naive Bayes classifier, it is easy and fast to predict the class of the test data point since you already have the probabilities for each outcome. Okay, it is if you just know what you want to predict, it's easier to get the class. You just check which probability is higher, okay, and then you can come to a conclusion. Then, since this is only using the Bayes theorem, can anyone tell me what's the meaning of naive? Naive. So naive means lack of, I would say, knowledge or experience or something. Okay. Here is an example showing only a single feature. Okay? But when many features comes into play, this formula becomes highly complex to calculate. Okay. But when we assume that the features are independent, independent means let's take uh, I take another feature here, let's say temperature. Okay. If I assume that temperature and weather, okay, those are two different features, they are not related to each other at all. Okay. So that's what the naive Bayes classifier assumes. My calculation, everything becomes easy. Okay. But in reality, that is actually not the case, right? Uh, Weather and temperature might have some sort of relation. Okay. That is one thing. But if the features are actually independent, if you choose the features in such a way that the features are actually independent and not related to each other, the naive Bayes classifier is actually the best machine learning model you can use for the classification task. Okay. And also, what are the type of variables in this case here? Is it numerical or categorical? Numerical, you would have numbers. What's the type of input or independent variable here? Is it numerical or categorical? Yes, it is categorical. Good. So if you have categorical variables as input, it's better to use naive Bayes in that case. And naive Bayes classifiers, they have already been applied to several downstream use cases for text classification, recommendation systems, text classification. I would say one example is uh, sentiment analysis. Okay, reading a passage, you can guess the tone of the writing, whether the person who's writing it is angry or like those kind of things. So sentiment analysis and recommendation systems, I would say you would be seeing ads in your social media like Instagram, Facebook, or something, right? That goes through all your uh, data, okay, and then comes into they again does some machine learning and recommends you some products that that you might actually buy. Those are all your recommendation systems. Or if you are simply watching Netflix or something, it will actually recommend you this movie, that you can watch this movie or something. Those are all your recommendation. systems. And naive-based classifiers, this is one of the initial algorithms that people were using in these kind of text classification and recommendation systems. Okay. Any doubts in naive-based classifier? Anything? If you still don't understand the concept, I can take another example also, I guess. Any doubts? Yeah. Okay, then I'll move on to support vector machines. Okay. This is something you can use both for classification as well as regression. The goal of support vector machine is to create the best decision boundary that can segregate any n-dimensional space into its corresponding classes. Okay. Here you have two features, x1 and x2. Okay, x1 and x2. You have two classes, class A and class B. Okay. Yesterday, when I was showing the notebook, I plotted something called the decision boundary, right? Anything above the decision boundary will be put into class one, anything below it will be put into class two. I was explaining all that stuff, yesterday. Same thing will I apply here. Okay. Here, what I want to do here is, and if you notice something yesterday, this some points were misclassified also. Some of the blue points were in the red zone, some of the red points were in the blue zone. We don't want that to happen, right? So here what support vector machine does is it calculates this maximum margin hyperplane. Okay. It tries to find this line that separates these two classes. Okay, and keep both of them apart as far as possible. Okay, the distance from this line to this point is what you call the margin. We want to maximize this distance and this distance also. Okay, this is the principle or goal of SVM. How it does that is a different thing. We won't be talking about that. We'll only be looking into the practical or coding aspects here. We won't be going into the uh, optimization, formulation, and all the mathematical stuff. Okay. The goal here is to find this line that can separate these two classes well, okay, with the maximum margin. Any doubts here? SVM. So naive base deals with probabilities. Yeah. SVM is an entirely different class. And these 2 points that you see here, they are known as support vectors. Okay. Any doubts here? Okay. Mm, moving on, this is a very simple example, similar data set here. Okay. And again, I have two features, x1 here, x2 here. Okay. Uh, how many different types of lines I can draw in between, this? Any guesses? How many lines I can draw that, separates these two classes? How many lines? How many lines I can draw that can separate class A and class B? The blue and green points. Just put some numbers that you can think of. Any number you can think of. Just put it in the chat box. Okay. I would say I can draw infinite number of lines that can separate these two classes. But which would be the best one? See, I can draw a line like this. I can draw something like this keeps on. I can keep drawing. But the best one, that the SVM can find is this particular green line. Okay. See, it has the maximum distance from this point and this point also. So here these 2 points are your support vectors, and this is the maximum margin. And this green line, yeah, you cannot say equal distance. Yeah, it is equal distance. Yeah, and that distance should be maximum also. Okay, and yeah, you can find a line that is equidistant from this point and this point also. But again, you should take the closest points, okay, to this line and make sure that distance is maximum. Okay. Any doubts here? Okay. Moving on. As this is your optimal line or hyperplane. Okay. These are your support vectors. Okay. This point and this point. It's equidistant and has the maximized margin. Okay. Uh, as I keep saying, our goal is to maximize this margin. Okay. Find the support vectors, the points that are close here, and maximize it. Find a line that is equidistant and has the maximum distance. Yeah. So, okay. And that is about SVM. And yeah, these are, these four algorithms that I was talking from yesterday are the basic machine learning algorithms that you can master to do either binary classification. Binary classification, I would say, deals with the presence or absence of something. Okay, just a single label you have, but the things can be multi-class also. Multi-class is I can have many different labels. Like in the fashion in this case, I have a bag, I have a shoe, I have a dress, I have a jacket. So I have multiple different labels. So that will be your multi-class case. And there is also the multi-label case. Okay, multi-label is in the binary classification case, you only have a single task. Multi-label case, you have different tasks. Okay, and each task you check whether you have presence or absence of something. Okay, let's take in the email spam classification case itself. You check whether it's spam or not. Okay, and then another task might be what topic is this email related to? Okay, is the email from administration? Is it from your uh, faculty member? So that might be one of it can be another task. Okay, so yeah, so there are three different types. One is the binary classification, one is multi-class, and the third one is multi-label. Okay? Whatever task you have at hand, this is the pipeline that you will follow. So these are called best practices in ML. Okay? You have to do the k-fold cross validation. So you this is your entire data set. Okay, you split it into k folds. Here I'm splitting into five different parts, equal parts. Okay, I keep the last four parts for training and keep the first one as validation. The blue one here indicates validation. Okay, you do the training, do the testing, you get your accuracy score. That is performance one. Okay, you repeat it for how many ever folds you want. Since I've split the data set into five equal parts, I am iterating it for five different times. Okay. I get all the accuracy scores, do the average, and that will be my final performance. Okay. That is the first thing that we'll be doing, getting a baseline. Then there is something called hyperparameters. Okay. Any hyperparameter you can think of that I was talking about in the previous classes. Any hyperparameter you can think of that I kept changing in between and see how the performance also changes. Hyperparameters you can think of uh, arguments where if you change that, the model performance also changes. Okay? You're not changing anything about the model. Okay? You're changing something about the learning algorithm. Okay, and yeah, any hyperparameter you can think of. Think of the polynomial regression case. Any hyperparameters that I kept changing. Any hyperparameters. I kept changing the degree of polynomial, right? As you can see, if I keep changing the degree, the model overfits, the test error keeps it became high. Okay. So the degree there is a hyperparameter that you can change. Similarly, there are hyperparameters for whatever ML algorithms you are going to learn. You have hyperparameters in your support vector machines. Okay, that I'll be showing in the coding session. Okay, you but I don't know which one gives the best performance. No, for me, which hyperparameter gives me the best performance? I don't know that beforehand. I have to keep trying different values. Okay, you can do it in a random way, or a random way I would say is you define a range. I want to try all degrees of polynomials between 1 and 30. Okay, but I don't want to run it 30 times. I'll only run it 10 times by randomly choosing like 10 different degrees between 1 and 30. That is one way of doing it. Okay. Then there is the brute force way, I would say, trying all possible combinations. Okay. So there is your random search. There is your the next one, the brute force way I'm talking about is the grid search. Okay. You try out all possible combinations of hyperparameters, then you check the performance here and then say this is the best model I can get. Okay. Choosing the appropriate hyperparameter is crucial for success. And yeah, you might think the default parameters might work best for you, but that is not the case most of the times. As your data set keeps changing, the best hyperparameter value also keeps changing. And to find the best hyperparameters, so this is what I would say is the tuning curve that you get. Okay, these uh, these are different hyperparameters. You don't need to worry about what the model here is used. And here, this bar represents the evaluation metric. Okay. You see, I try uh, the so you can consider three different, you know, hyperparameters I have. Okay. If I choose this as zero point 0.4, this as 1, and this as zero point 0.2, my evaluation metric is around 0.47. Okay, and all these curves that you see here are different experiments. I keep on repeating it with different values here. And how do I find the best one from here is I take this one and I try to trace it back. So the best hyperparameter for this one is zero point 0.2. If I go a little back here, this one I should choose as 2. And if I go back here, this I should put it as 0. Okay. Yeah. Then, this is how you interpret the results of this plot. And you can see how much the difference is. If I keep everything as 0, 1, and somewhere near to 0.01, my metric here is actually low. And you see there is a huge difference. Changing these three values alone, I'm not changing the model. I'm changing the hyperparameters in the model. How much difference I'm getting here. See? And this is why I say picking the hyperparameter is crucial for success. And this is kind of like an overview. Okay? And these are different types of hyperparameter search methods that you can use. I would say for basic use cases where you have only, let's take only these three hyperparameters, your grid search and random search can work best. Okay. Grid search, all combinations are tested. Grid search, all combinations are tested, random search, you would say I can only do 10 experiments. I can't do anything more than that. Okay. If you are talking about it that way, I can randomly choose hyperparameters 10 different times, keep running and get the hyperparameters that actually has the maximum performance. Okay. Then these again, these are more complex search methods, the Bayesian optimization, genetic algorithms, and particle swarm optimization. Okay. Here, what they do here is again, I can only do 10 experiments, but I'm not randomly selecting any values. Uh, they have a predefined set of criteria to choose the best hyperparameters. Again, these all can't guarantee that you will always get the best performing hyperparameters. But I would say grid search, if you try all combinations, all possible combinations, even though it's computationally difficult or not efficient, I would say grid search can always return you the best possible hyperparameter combination instead of these methods. Okay. And yeah, you do hyperparameter tuning, apply whatever search method you have, do cross validation, get average accuracy, get the accuracy passed to the search algorithm, and keep repeating this loop unless until you have the best performing model. Okay. Maybe I can give you some use cases. I only have three hyperparameters, and each hyperparameter, say I have 10 different values to be tested. Which one do you think? I have all the, no, I can do any number of experiments I can do, any number of experiments I can do. Which one do you think should I select here? Which search method I should go for? I only have three hyperparameters. Each hyperparameters has 10 different values. Okay. I can perform any number of experiments. That is not an issue for me. So which search method should I go for? Which search method I should go for? You have five options. You can type anything. Okay. I can go for grid search. If I have 50 different hyperparameters I want to test for, and each one has around 100 values, I can only run experiments 50 times. Okay. Each run. I can only do 50 runs. Then I would go for Bayesian optimization. Okay. Scikit-learn has the grid search and random search method already implemented. If you want to take a deep dive into all the other search algorithms, I would say you can look at the Optuna package in Python. Optuna, just yeah, But for basic use cases, grid search and random search would work perfectly fine. Okay. Any doubts? Any, you have any doubts in naive Bayes, SVMs, tuning method, anything? So today what we learned is two new algorithms for classification. Naive Bayes is the ideal classifier if the features you are using are actually independent. Okay. Naive Bayes is probabilistic in nature. You compare probabilities for both the labels, and then whichever has the highest probability, you give that label as your output. SVM uses the maximal margin hyperplane. You have two classes. You want to find a line that has the maximum margin, okay, based on the support vectors. And you should always tweak your hyperparameters to get the optimal result. Okay. SVM, uh, maybe it was easier for you all to visualize it, the two-dimensional case. What if we go to n dimension, let's say 3D? Okay. How can you find the support vectors? Or yeah, or one more thing. I have points, I have blue points here also. I have green points here also. Do you think SVM can work in that case? I have some blue points here, I have some green points here also. Do you think SVMs would work in that case? Okay. So the linear SVM would not work actually. There are nonlinear versions also, uh, but I won't be going into the details of it. And yeah, nonlinear SVMs, what they do is they somehow use a transformation. Okay, they transform these coordinates into some other coordinate space. Okay, there you can actually get the separation. Okay, like this. Even if some points are here and some points are here. So that would be your nonlinear SVMs. Okay. Any doubts till now? Any questions? You can ask anything. Anything about previous classes also. Am I going too fast or is this pace okay for you all to follow? Or do you all need more details for all these algorithms? Just anything you can let me know in chat. Okay, can I move on to the coding session? Okay. Okay. So here I'm going to implement naive Bayes and support vector machines. So here from scikit-learn.naive Bayes, you import the Gaussian naive Bayes class. Here from SVM module, I am importing support vector classification SVC. Okay. I'm making a binary classification dataset. Okay. Um, I'm doing the train test split, everything like I did in yesterday's class. Okay. I'm creating a naive Bayes classifier. I'm doing training using fit. See, I only use X train here, Y train here for training. I don't use X test and Y test. You shouldn't do that. Okay. Then make predictions. Predictions, I do it on X test. Get the accuracy score. Okay. You have your labels, you have your predictions. I'm printing it. Okay. And then in this specific block of code, I'm plotting the decision boundary. Okay. You don't need to worry about this block of code since that is just for your visualization purpose. Okay. We'll run this. Here again, I'm doing a scatter plot of this specific data. Okay. So scatter plot, first feature, second feature. Here for class 0, I'm doing y is equal to 0 for class 0. Here I am doing it for class 1. Okay. Feature 0, feature 1, feature 2. I'm just setting the title, I'm setting the labels, I'm getting the legends, and finally I'm showing the plot. You see, this is how it is. My accuracy is 90%. Is this good enough? Hmm? See, some points here are misclassified. Here, this is the decision boundary for blue, this is for red. Some blue points here are not classified well. Here, again, some red points are in blue region. Okay. Let's see how our SVM does. Okay. SVM here again, it tries to put a straight line. I think it would put output this line. Let's see. Okay. I'm putting the kernel as linear. Linear SVM, make sure that you just draw a line. Okay. I'm doing fit. I'm predicting, calculating accuracy score, plotting the same data set. Okay. And you don't need to worry about this part of the code also. I'm just drawing the support vectors, okay, and the maximum margin hyperplane in this specific block of code. Okay. I'm setting the title, labels, legends, and I'm showing. See, this is the best possible, you know, margin it can get. Okay. This is my support vector and this is my support vector. These two. Okay. Any questions? Any questions here? If you want to do regression using support vector machine instead of SVC, you can import SVR and do regression. That's it. That's the only difference. Okay. My accuracy is 95%. Okay. Can I improve this? Can I improve this? Can I tweak some hyperparameters that can, push my accuracy towards 100%? Can I do something? So one more thing I was talking about during the lecture is the type of SVM I can use. Here I've used linear kernel. Can I use some non-linear kernel? Non-linear SVM. Can I do that to improve my performance? Let's see what all height arguments Gaussian naive Bayes has. Okay, it only has priors. You don't have information on that. Variance smoothing, again, you don't care about that. Gaussian naive Bayes, you can't change anything. Okay, Gaussian naive Bayes, you can't change anything. It doesn't have any hyperparameters. Okay, but let's look at the case of support vector machine. You have C, you have your kernel, you have this many options. See, you have degree of polynomial that you can use. I was talking about it in the lecture. You can change gamma value. You can change this. And yeah, I think rest all would be fine. Those are not hyperparameters, but you can change all these. Okay. And then you can check, you can run different experiments. So here again, if I put kernel as poly, mm, this is one. Okay. My degree as 2, C as 1. That's it. Okay. Let's see if it changes. See, this is how it changes. Since this is a non-linear kernel, I have a line running like this and there are many points that are misclassified. My accuracy changed to 0.45. This is bad. I don't want this. Let's try RBF. This is another kernel I'm using. See, 100% accuracy. If I see here, this is my line. Anything here, all red. Anything here, all blue. These are my support vectors. I think there's one misclassified point, but I think that would be like 999. So I think it's one. Yeah. This is a better model, right? Using RPF. Let's change the value of C to 5. Again, 100%. Should not be 0. See, I change C. Accuracy is 45%. And this is my model SVM. This is my maximum margin hyper. It's very bad. You can understand here, right? How important hyperparameters are. Whatever model you have, the performance depends on whatever hyperparameter you set. So you have to try out different combinations, but writing code for trying out all combinations is very hard. That's why scikit-learn has a convenient grid search CV class. I'm going to do grid search. I'm essentially following the slide that I showed you all, the final overview of all the tuning methods and stuff. Okay. CV here refers to cross validation. I will split my data set into five specific folds. Let's see what the default parameters are. CV, yeah, the default K here is 5. Okay, you split it into 5 equal splits. Take 4 for training, 1 for testing. You repeat the thing 5 times, you get the average score. Yeah, that's it. Okay. Everything you don't need to code by hand. You have the grid search CV class. Here I'm defining the parameter grid. Can anyone recognize what data type this is? What's the data type used? What is the data type of parameter grid? Yeah, dictionary. So if you want to search for C, I'm mentioning here, I want to try these different values for my hyperparameter C. For gamma, I want to try all these values. For kernel, I want to try the linear kernel. I want to try the RBF kernel. Okay. I instantiate the grid variable, grid search CV. I pass in whatever model I want. It can be a support vector machine, it can be a neural network, and so on. Any model. Okay. And accordingly, you have to change the parameter grid. So the keys will be whatever hyperparameters you want to change. C, C. Okay. Kernel, kernel. And in this, you give a list of all the values that you want to test for. Okay. I do again same fit. I do fit on train, get the best parameters. Okay. For that specific run, do prediction, do testing. Okay. Get the accuracy score. Do you think if I run this, I will get 100% accuracy? Yes or no? See, I may get it, I may not get it. Okay. Since because I have not tried all possible combinations of C. I didn't put 0.01. Maybe that might give me the best possible performance. Gamma here, I didn't try 10, value of 10 here. I didn't try the polynomial kernel. So this is something you should look for. The parameter grid that you define should take into account all possible values that might give you the best performing model. Okay. But since this is just a demonstration, I'm just putting in these values. And grid search CV, it's not, it is computationally expensive to run because maybe in the first run, it will check the value, accuracy score when it's 0.11 linear, then it will try for 0.11 RBF, then it will try 1 linear, 1 RBF. It will try all possible combinations. Grid search CV. Or else, if you don't want to run it, you can do randomized search CV also. Randomized search CV, uh, you have to mention number of iterations or number of runs you are willing to do. Okay, n item. Okay, and it will randomly pick points. Maybe in the first run it can pick 10.01 in RBF. Second run it can pick 1000.1 in linear. But when you only do 10 iterations, it might obviously miss some combination that can give you the best possible performance. So that's the disadvantage of randomized CV. Randomized CV, you can control the number of iterations, it's faster, but it's not as comprehensive as quick search CV. Okay, using quick search. Let me run this. Okay, my accuracy after hyperparameter tuning is 100%. Yeah, see, and how many runs it has done. It has tried this and got 0.938 as score. It has tried this combination again 0.938. See, with this combination, it got 100% score. But see, it's for first fold. Okay, so it's 0.938, 938, 1, 1.938. Okay, you take the average of all this, then only you can know. Okay, so here you are testing it for 50 different combinations, 50 candidates, and each run you repeat it for 5 different folds. So total you have 250 runs, 250 experiments you are doing. Okay, only if you do all 250 experiments, finally you get the. So these are my best possible hyperparameters, and my best possible accuracy is 100%. Okay, any doubts till here? If I give a real world data set, will you all be able to run this code? Okay, do hyperparameter tuning. Maybe at the end of this course, I'll set up a hackathon kind of thing where I'll give you all a data set. You, whatever algorithms you all have learned, you try to implement it, try to do hyperparameter tuning, and yeah, whoever gets the best possible score, uh, yeah, that will be good for them. It'll be a good exercise for you all to do it. Here I'm just using a randomly generated data set. Maybe you can all find real world data sets. One specific resource I recommend is Kaggle. Okay, you can look at all the tabular data sets available in Kaggle. Okay, you just have to make a modification to this specific line. That's it. Rest all will work. You can comment out the plotting uh, code also. You have to run this part, just this part. You define your X and Y, whatever data set you have, you define it, run this, that's it. You don't need to do anything different. If you want to change different models, change this specific line here. Okay. And I have again posted the link in the same link to the notebook in the same Google Drive link that I shared yesterday. Maybe you all can give it a try. Maybe I can stay here for 10 more minutes. If you all have any doubts in the notebook, you can ask. You are free to me if you don't have any doubts in the notebook or the lecture. Tomorrow, Pratyay, he'll be talking about decision trees. Those are again a separate class of algorithms where again it can be used both for classification and regression. He'll be giving you all an introduction to all the different types of trees, backing, boosting, and other stuff. Thank you all for attending. Just stay here for a few more minutes if you all have any doubts.